The second type of variation problems we want to consider are referred to as inverse variation problems. In this case, we will end up setting up an equation of the form y equals k times 1 over x, meaning those variables vary inversely. As one gets larger, the other is getting smaller, and vice versa. In example 4, we're told to suppose that the demand D for candy at a theater is inversely related. So those would be some keywords that we would look for to know we're dealing with this inverse variation situation. Inversely related to the price P. So that means we can set up the equation D is equal to some constant K we'll need to solve for times 1 over P. Since again we have that inverse relationship. When the price of candy is $3 per bag, the theater sells 210 bags of candy. So that demand in this case would be 210, which would be equal to that constant K times 1 over the price of $3. Multiplying both sides by 3 would give us K is equal to 630. So our formula is going to be D equals 630 times 1 over P. Or we could rewrite that as 630 over P. We're told to express the demand in terms of its price, and then determine the number of bags of candy that would be sold if the price is raised to $3.50 a bag. Which means we would take that 630 and now divide by this new price of $3.50, or 3.5. And our formula would tell us that we can expect to sell 180 bags of candy. In example 5, we're told that the weight of a body above sea level varies inversely. So again, that's another way to indicate that we have this inverse variation situation going on, to the square of the distance from the center of the Earth. So this lets us know that we can set up an equation of the form W for weight equals some constant K times 1 over D, that distance, and in this case, squared. So in both of these examples, we're dealing with nonlinear relationships. Since our independent variable is in the denominator, and in this case, we have that denominator, that independent variable, also being squared. So in examples 4 and 5, we're actually dealing with nonlinear situations, but we're still getting practice with this idea of setting up equations and translating the information from story problems into those equations. So we're given some information to plug in this case a person who weighs 138 pounds when they're at sea level, which is 3,960 miles from the center of the Earth. Is going to give us a value of K equal to 2,164,060,800, which means we can complete our formula by substituting in that same value for K over our distance squared. And then we're asked how much will they weigh when they're at the top of a mountain, which is 1.9 miles above sea level. So we'll have that same value that we found for K, a little over 2 billion. And what we'll substitute in for D in this case isn't that 1.9 miles above sea level, but actually 3,960, which is the distance from sea level to the center of the Earth, plus that additional 1.9 miles that they are above sea level, that value squared. So what we'll be substituting in will be 3,961.9, which will give us approximately 137.9 pounds. So again, while we're primarily focused on linear models for right now, it's not too much of a stretch to look at these inverse variation problems or look at those direct variation problems where we're relating to variables where one of them is being squared, to again get in the practice of just constructing these equations, in these cases solving for some unknown, and then applying that equation to either find an unknown value for the dependent variable or the independent variable.